Okay, let's unpack this. Today, we're diving into, well, the fascinating, often unseen world that powers our industrial systems.
Hmm.
We're talking everything from, sprawling factories to the complex machinery keeping our infrastructure humming.
Right, the stuff that just works behind the scenes.
Exactly. And if you've ever wondered how these huge operations stay synchronized, how they stay so efficient, you're about to get some serious aha moments. We're really getting into the brains behind it all.
Yeah,
We're taking a deep dive into the standards governing industrial control. First up, the foundational one, IEC 611313.
it's a classic.
And then where things get really interesting, I think, is its evolution into IEC 61499. That's a standard really designed for the future for distributed systems.
Let's look ahead.
So our mission today, basically distill these pretty technical concepts into clear, actionable knowledge, give you a shortcut to being well-informed about the computers, really, that run our world.
And it's remarkable, isn't it, how these standards aren't just about programming rules. They represent a fundamental shift, a paradigm shift in thinking about automation.
How so?
Well, we're moving from that old model, the centralized command and control, to something much more agile, more interconnected,
Okay.
which raises this really crucial question. How do you build these incredibly complex systems where, individual parts have their own intelligence
Yeah.
and they communicate seamlessly and act like one unified thing?
Right. How do you orchestrate all that?
Precisely.
Yeah.
And that's what we're going to uncover today.
All right. So let's start with the basics then. The workhorse. The PLC.
Ah, yes, the
Oh.
PLC.
Programmable Logic Controller.
For anyone listening with maybe a software IT background, you could almost think of a PLC like a Raspberry Pi or an Arduino, but that's not quite right. It's really purpose-built, super rugged, designed for tough industrial environments.
It's a totally different beast, yeah. Built for reliability. It's got dedicated inputs, for sensors, buttons, things like that, and outputs for controlling motors, valves, whatever it might be.
Mhm.
But the key difference is efficiency for a narrow purpose, which historically meant manufacturers developed the hardware, the firmware, the basic software, and even the specific development tools just for their PLCs. Very siloed.
And that point's critical. When you connect it to the bigger picture of programming these things traditionally, each vendor gives you their own IDE, their integrated development environment.
Right, the proprietary software.
Exactly. That's where you write your application, which is just the user logic for that specific PLC.
Yeah.
Then you hook up your computer, often with an Ethernet cable now, upload the application,
And deploy.
and deploy it. Once it's on there, it just runs whenever the PLC is powered up. And this whole world, this ecosystem, has largely been governed by that first standard we mentioned, IEC 61131-.
Okay, now this is where, for me, it gets really interesting. Because even though you had all these different PLC vendors, different hardware, different IDEs, the actual programming languages got standardized under 61131-3.
Yeah, that was a big step.
We're talking 5 distinct ways to program. The graphical ones, ladder diagram,
Looks like electrical schematics, yeah.
dash function block diagram, and sequential function chart. And then the text-based ones, structured text,
Which looks a bit like Pascal or C.
and instruction list, although IL is pretty much deprecated now, right?
Yeah, you don't see IL much anymore.
Yeah.
But the key thing, like you said, is they're different from general-purpose languages like C++ or Python. They have a much higher level of abstraction, especially the graphical ones. And what's really striking about those, particularly function block diagram, or FBD, is how they simplify complex logic.
Oh, so?
Well, imagine a function block, an FB, as like a pre-engineered component, a
Yeah.
little black box you can trust.
Okay, like a timer or a counter.
Exactly.
Yeah.
Or a latch, something that performs a specific encapsulated task. Inputs on the left, like parameters, outputs on the right, like results. And an FB can have multiple outputs too.
Right.
So you could have, say, a basic RS flip-flop block. You feed it a set signal, the output turns on. Feed a reset signal, it turns off. Simple, visual, modular. This was revolutionary for building reliable control systems back then.
Okay, so that lays the groundwork. That's the foundation. But as you said, industry is moving on. Industry 4.0, industrial IoT, that means centralized control is, well, kind of struggling.
Its limitations, yeah.
We're moving to distributed systems, individual components with their own smarts talking to each other. And this is exactly where IEC 61499 comes in as the newer, more adaptive standard. So for someone learning this, what does this evolution actually mean? What are the practical improvements?
Well, that brings up a really important question, doesn't it? What were the actual problems, the real pain points with 611313 that made a new standard necessary?
Yeah, what wasn't working?
Two big things really stood out to engineers. First, those feedback loops you sometimes need in control logic. In 611313, how they actually behaved could be unpredictable, depending on the vendor's underlying software implementation.
Ah, so debugging could be a nightmare.
Oh, absolutely.
Yeah.
Like trying to solve a Rubik's Cube blindfolded, someone once said. You might get there, but it wasn't smooth or predictable.
Okay, what was the second thing?
The second big one was interoperability. If you tried to mix PLCs from different manufacturers in one system, well, good luck getting them to talk to each other smoothly. Communication wasn't really standardized at that level.
Right, vendor lock-in was a real issue.
Huge issue. So IEC 61499 directly tackles both of those head-on.
And it really does seem to. I mean, 61499 extends the old standard by first radically improving how software components are encapsulated, making them much more reusable.
Better building blocks.
Second, providing a truly vendor-independent format. And third, fundamentally simplifying that controller-to-controller communication.
Yeah, it's a different philosophy.
It defines this domain-specific modeling language. It builds on the function block idea we talked about, but it's specifically geared towards distributed systems.
Right, so you can model the whole thing.
Exactly. You can model the entire system, even if it's made up of, say, dozens of smaller PLCs working together. And a core principle here, which I find fascinating, no global variables allowed.
Ah, that's key.
Yeah, it powerfully reinforces that encapsulation. All the functionality stays inside each function block, makes the behavior way more predictable. It's kind of like bringing a microservices architecture to industrial control.
That's a great analogy, actually.
So let's dig into the nitty-gritty then. How do these IEC 64499 function blocks actually work? You mentioned they look different.
They do. The interface is clearer, inputs are still on the left, outputs on the right, but there's this crucial differentiation now, events and data.
Okay, events and data, how do they look?
Events are usually shown as red lines connecting to the top part of the block. Data connections are blue lines on the lower part.
Red for events, blue for data. Got it.
And events are the triggers. They kick off the FB's functionality. The FB then uses whatever data is available on its data inputs at that moment.
So the event says go, and the data is what it works with.
Pretty much.
Yeah.
And here's a really crucial detail. Event connections and data connections are totally separate. You cannot connect an event output to a data input, or vice versa. They're incompatible by design.
Interesting. Keeps things clean, I suppose.
Exactly. It
Yeah.
enforces a clear flow. And another key innovation is how they handle fan-in and fan-out.
Okay, explain that.
Right. For data connections, fan-out is fine. One data output can feed into several data inputs on the next blocks. Makes sense, right? You calculate a value, lots of things might need it.
Yeah, okay.
But fan-in for data, not allowed. You can't have multiple data outputs trying to connect to a single data input.
Right.
Causes confusion.
Right, which value wins.
Exactly. But now, for event connections, it's different. Both fan-in and fan-out are perfectly okay.
Ah. So multiple events can trigger one block, or one event can trigger multiple blocks.
Precisely. This gives you huge flexibility in designing the control flow, the triggering logic. And the whole behavior, what the FB actually does when an event arrives, is governed strictly by its internal event execution control, or ECC.
Okay, the ECC, that sounds important.
It is. It choreographs everything. Which internal functions run, in what order, and when output events get sent out.
So when an FB gets triggered, how does that choreography, that sequence actually play out? Is it fixed?
It's very well defined and predictable. An input event arrives, step one.
Okay.
Then the data associated with that event on the connected data inputs gets refreshed, basically read in.
Got it. Read the data.
Then that event signal goes to the ECC, the brain inside. The ECC decides, based on the event and its internal state, which internal functionality to trigger.
Runs the code.
Runs the right piece of code, yeah.
Yeah.
That code then calculates and provides new output data values.
Updates the results.
Updates the results,
Yeah.
then specifically the output data values related to the output event that's about to be sent are refreshed.
Okay. Prepares the outgoing data.
And finally, the corresponding output event is sent out, triggering the next block in the chain.
Event in, data read, logic runs, data out, event out. Seems logical.
It is. And what's crucial for reliability is that some of those internal steps, like running the internal logic and providing output data, can actually repeat multiple times within a single event processing cycle, all orchestrated by ECC in a predictable way.
Wow, okay, so it's not always just a single pass-through.
Not necessarily. Depends on the logic defined in the ECC.
Now, zooming out a bit, you said one of the huge advantages of 6.499 is support for distributed applications. How does that actually work?
Yeah, this is where it really shines from modern systems.
Yeah.
You can design one large logical application,
Okay.
and then you can decide to split it up, deploy different parts of that same application onto several different physical devices, different PLCs.
Ah, so the logic isn't tied to one box anymore.
Exactly. You can even have multiple applications running concurrently, with parts of each spread across many different devices. It's incredibly flexible.
How do you manage that complexity? How do you design that distribution?
The standard includes what's called a system model view. It's a high-level perspective that helps you map the logical application components onto the physical hardware configuration.
So you visually plan where things run.
You do,
Hmm?
but there's an important rule. A single function block, one of those individual components, cannot be split across devices. It has to run entirely on one device.
Okay, the blocks themselves are atomic in that sense.
Right. But a single physical device, a PLC, it can run many different applications, or many parts of different applications, all at the same time. It does this by using its internal resources.
Resources, what are those like?
You can think of them kind of like execution threads or separate processing environments within the PLC.
Hmm.
Each resource can host and run parts of your applications.
I see. So one PLC can multitask different application pieces.
Correct.
But wait, if you split an application across different PLCs, how do you maintain the connections? The event and data flow between function blocks that are now physically separated.
Excellent question. That's where the concept of broken connections comes in. When you split the application in the system model view, the connections between blocks on different devices are, well, notionally broken.
Okay. Sounds like a problem.
But the standard has a very elegant solution. It automatically handles these using special function blocks. Publish and subscribe FBs.
Publish, subscribe, like MQTT or something.
Conceptually similar, yes.
Yeah.
These pub sub-blocks aren't part of your main application logic that you designed. You see them more in the background of the resource view. They act like the invisible plumbing.
How do they work?
When an event and its data need to go from a block on device A to a block on device B, the connection hits a publish block on device A. That block takes care of sending the event and data over the network using whatever communication protocol is configured.
Okay, it broadcasts it, basically.
It publishes it, yeah. Then, on device B, a corresponding subscribe block is waiting. It receives that event and data from the network and passes it along to the target function block on device B, just as if it were a local connection.
Ah, very clever. So it bridges the physical gap seamlessly.
Exactly. It ensures that communication just flows automatically between
Ah.
the different PLCs in your distributed system. It even handles communication with things like HMIs, the human-machine interfaces. It really enables that plug-and-play communication for distributed control.
That is pretty powerful. Okay, so let's talk a bit more about the function blocks themselves. You mentioned they have different personalities. What are the main types in IEC 61499?
There are three main flavors, each with a specific job. First, the most fundamental one, the basic function block, or BFB.
Basic function block. Okay, the workhorse.
Pretty much. This is where you define the core custom logic for your process, the secret sauce, if you like.
And how do you define that logic inside a BFB?
It uses that execution control chart, the ECC that we mentioned earlier. The ECC is essentially a state machine.
A state machine, like idle, running, error.
Exactly like that. You define the states your process can be in. Then, within the ECC, you define transitions between those states based on incoming events. So, if I'm in the idle state and I receive a start event, then transition to the running state.
Okay. And what happens during a state or a transition?
When the ECC enters a state or performs a transition, it can trigger specific internal algorithms. These algorithms are the actual code, often written by the user in a language like structured text from the old 61131 standard.
Ah, so you still use those languages inside the BFB.
Often, yes. The ECC orchestrates which algorithm runs and when, based on the state and the incoming event. It also defines exactly when output events should be triggered.
And transitions can have conditions too, right?
They can, yes. A transition might only happen if an event arises and some data condition is true, like temperatures above 50 degrees. And a really important point, an input event is consumed only once by a transition. It triggers one specific path in the ECC.
Got it. Very structured way to manage complex logic. So that's the BFB. What's next?
Next up is the Composite Function Block, or CFB. This one's actually simpler conceptually.
Okay.
The CFB is essentially just a container, It doesn't have its own ECC or internal algorithms.
Oh, what does it do?
It holds an internal network of other function blocks. Those blocks inside could be BFBs, they could be other CFBs, or they could be the third type we haven't discussed yet.
Ah, so it's for grouping things, building bigger components out of smaller ones.
Exactly. It's all about hierarchy and reuse. You build a complex piece of functionality using several BFBs and maybe other CFBs, wrap it all up in one CFB, and now you have a single reusable component that hides the internal complexity, like nesting functions or creating classes in programming.
Makes sense. Build complexity layer by layer. Okay, and the third type?
The third type is the Service Interface Function Block, or SIFB.
Service interface. That sounds like it connects to the outside world, maybe. The hardware?
You got it. That's precisely its role. If you step back and think about it, these applications running distributed across devices need to interact with the real world, right?
Yeah, sensors, actuators, network ports.
Exactly. They need to access physical inputs, drive physical outputs, or use specialized communication hardware, like that Ethernet port. That's where SIFBs come in. They provide that bridge between the software logic and the underlying hardware or system services.
So they're like device drivers, almost.
Kind of, yeah, or adapters. What's unique is that an SIFB can be activated not just by an event coming from another FB in your application,
Okay.
but it can also be triggered directly by the hardware itself.
Oh, interesting. How does that work?
Well, imagine you have an SIFB designed to handle incoming network packets, maybe a responder SIFB. The arrival of a physical packet on the Ethernet port could directly trigger an event output on that SIFB.
Ah, so a hardware event directly injects an event into your 61499 logic.
Precisely. It directly links hardware events or system services into your control application's event flow. This is absolutely crucial for building responsive, real-world systems.
That really closes the loop between the software model and the physical reality. But it does raise a question, thinking about different vendors. If SIBs talk to specific hardware, how do you ensure different vendors' hardware and the SIFBs designed for them actually work together in a predictable way?
That's a fantastic point and leads directly to the next piece of the puzzle. The core IEC 61499 standard itself is, by design, quite abstract.
Right, you said it gives flexibility.
It does. But that means it doesn't explicitly define everything you need for a real system to run. Things like, the exact communication protocol to use between devices, or the specific way an SIFB should interact with a particular type of I/O card.
So there are gaps.
Intentional gaps, yes, left for flexibility. But obviously you need to fill those gaps for systems to actually work and, crucially, interoperate.
So how do you handle those missing pieces?
This is where compliance profiles come into play. The standard itself is clever, doesn't define the specifics, but it specifies how those specifics must be defined.
Okay, so it standardizes the way you fill the gaps.
Exactly. Think of a compliance profile as a detailed specification document that layers on top of the abstract 61499 standard. It provides the concrete rules for things like communication protocols, device models, how SIFB should behave for common services, and so on.
So if two vendors both adhere to the same compliance profile,
then their IEC 61499 compliant devices and software tools should interoperate seamlessly because they've agreed on how to fill those abstract parts of the standard.
that makes sense. It bridges the gap between the abstract standard and a practical working system. Are there examples of these profiles?
Yes, absolutely. A well-known one, especially for showing the concepts, is the IEC 61499 Compliance Profile for Feasibility Demonstrations, which was provided by an organization called HoloBlock Inc. It lays out specifics for things like UDP communication for the publish-subscribe blocks, making it possible to build real, albeit demonstrator, systems.
Got it. So the profile provides the concrete implementation details needed for true interoperability.
That's the core idea, yes. It turns the abstract potential of 61499 into practical reality.
Okay, wow. So let's try to wrap this up. What does this all mean for you listening? We've journeyed through quite a bit here.
We have.
From the foundations, the PLC, and the original standard, IEC 61131-3 with its different languages,
Ladder FBD structured text.
to this really cutting-edge, distributed way of thinking in IEC 61499. We've talked about function blocks as these modular building blocks, BFBs, CFBs, SIFBs,
The different types.
and how applications can now be split up and deployed across loads of different devices, all communicating seamlessly using events and data and those clever publish-subscribe blocks.
Yeah, it's a big shift.
So what's the bigger picture takeaway here?
Well, the broader implication, I think, is that Understanding these standards, especially the direction 614909 is heading, mean understanding the real backbone of modern industrial automation. It's the underpinning for Industry 4.0 and the industrial IoT.
It's enabling that future.
It really is. That shift towards distributed intelligence, highly encapsulated functions, truly vendor-independent communication, it promises systems that are much more robust, much more flexible, and critically more scalable for the future. It's solving real-world problems engineers have wrestled with for decades.
It's incredible engineering, really, when you think about what keeps our world running. Okay, so as you, the listener, think about the future of automation, all this push for smarter systems, maybe consider this. In a world that's getting more and more interconnected with intelligent machines and devices everywhere, how might these core principles we talked about, event-driven logic, distributed control, encapsulation, as defined by IEC 61499, how might they reshape industries beyond just manufacturing? Could we see these ideas fundamentally transforming, say, smart cities or our energy grids, maybe even personalized healthcare systems?
That's a fascinating thought. Where else could this model apply?
Exactly. Definitely something to mull over.